Perhaps a radio signal detected from Proxima Centauri is that they detected it in a very narrow band of frequencies from the habitable zone, from a transmitter on the surface of Proxima b. This is the planet that orbits Proxima Centauri. Then I calculated that the frequency would drift. Imagine a world orbiting the star closest to our solar system, where liquid water might flow, yet relentless radiation could strip it bare. This is Proxima b, a planet that challenges everything we know about habitability. The discovery of Proxima b, a rocky planet orbiting Proxima Centauri, is a major milestone in the search for habitable worlds. What makes Proxima b so intriguing is its location in the habitable zone of its host star, where liquid water could potentially exist. However, habitability isn't just about location. The planet's ability to support life depends heavily on the intense radiation it receives, from X-rays to ultraviolet and infrared light. Understanding this radiation is critical for assessing whether Proxima b can retain an atmosphere, sustain surface water, or even host life. This video has two main goals. First, to explore the radiation environment of Proxima Centauri and quantify what reaches Proxima b. Second, to refine our understanding of Proxima Centauri itself, its mass, size, temperature, and brightness, as these factors shape the planet's potential for habitability. By combining observations across wavelengths, from X-rays to infrared, this research provides a detailed look at the star's emissions and their impact on Proxima b. The Proxima Centauri system and its importance. Proxima Centauri, located just 4.24 light-years away, is the closest star to our Sun. As a red dwarf of spectral type M5.5, it is much smaller, cooler, and dimmer than the Sun, with only 12% of the Sun's mass and 15% of its radius. Proxima Centauri's surface temperature of about 2,800 K is far lower than the Sun's 5,780 K, shifting its light output toward red and infrared wavelengths. Despite its dimness, Proxima Centauri's proximity makes it ideal for detailed study. Proxima b, the star's closest known planet, orbits at just 0.0485 Australian dollars, closer than Mercury's orbit around the Sun. Yet, because Proxima Centauri is so faint, this distance places the planet in the habitable zone. Proxima b receives about 877 W/m superscript 2 of stellar energy, roughly 64% of what Earth gets from the Sun. However, Proxima Centauri's intense activity, marked by frequent flares and strong stellar winds, raises critical questions about the planet's ability to retain an atmosphere and sustain life. Mapping Proxima Centauri's emission spectrum. The study of Proxima Centauri's spectral energy distribution is crucial for understanding the potential habitability of Proxima b, the exoplanet orbiting this red dwarf star. Proxima Centauri is known for its variability, particularly in the form of flares that significantly increase the levels of high-energy radiation, such as X-rays and extreme ultraviolet (UV) radiation. These stellar flares are much more frequent and intense than those of our Sun, and they can have a substantial impact on the atmosphere of Proxima b. Proxima b's close orbit within the habitable zone exposes it to a considerable amount of radiation. While the star's output is much lower than the Sun's in terms of visible light, its heightened emission in the XUV spectrum has important implications for atmospheric chemistry. High-energy radiation can break apart molecules in the atmosphere, leading to the loss of lighter elements such as hydrogen. Over time, this could result in atmospheric erosion, particularly if Proxima b lacks a strong magnetic field or a protective thick atmosphere. The radiation intensity, however, isn't just a threat. In combination with thermal radiation in the infrared, the energy input from Proxima Centauri also has the potential to shape the planet's climate. Infrared radiation from the star warms the planet's surface and atmosphere, influencing the greenhouse effect. In turn, this affects the planet's ability to retain heat, regulate temperatures, and maintain a stable climate for potential life forms. The study's integration of data from multiple instruments helps build a more comprehensive picture of the radiation environment around Proxima b. By analyzing the star's X-ray and UV flux in detail, scientists can estimate the amount of stellar energy available for atmospheric heating and determine the likelihood of atmospheric stripping. Similarly, observations in the infrared spectrum allow researchers to model how Proxima b might retain heat, especially in the face of such intense radiation. Ultimately, these combined observations inform our understanding of how Proxima b's atmosphere might behave in response to its host star's radiation. The planet's potential to sustain liquid water or harbor life is significantly influenced by these radiation interactions. Although the high XUV radiation levels present challenges, there could be regions on Proxima b, perhaps in its twilight zone or deeper in its atmosphere, where conditions are more stable and potentially habitable. However, the balance between radiation-driven atmospheric loss and thermal retention will likely play a central role in determining whether Proxima b could sustain life as we know it. The evolution of Proxima Centauri's radiation. To explore Proxima b's potential for habitability, it's essential to understand both the stellar environment it resides in and the planet's atmospheric evolution. Proxima Centauri, a red dwarf star, is much smaller and cooler than our Sun, but it is also highly active in terms of X-ray and ultraviolet radiation. This radiation plays a key role in the development and retention of a planet's atmosphere, particularly in the early stages of its formation. Red dwarfs like Proxima Centauri can be very volatile, emitting intense flares and XUV radiation early in their lifetimes. This period of activity, often referred to as the pre-main sequence phase, can last for hundreds of millions to a few billion years. If Proxima b was exposed to these early bursts of high-energy radiation, the planet's primordial atmosphere, if it had one, could have been stripped away, making it less likely to retain water or life-sustaining gases. However, after this initial active phase, red dwarfs like Proxima Centauri typically settle into a quieter phase where their radiation output stabilizes or decreases significantly. This creates a second phase in the planet's history, where the possibility for atmospheric recovery may emerge. If Proxima b experienced volcanic outgassing, where gases like water vapor, carbon dioxide, and nitrogen are released from the planet's interior, this could have helped build up a secondary atmosphere. Alternatively, impacts from comets and asteroids, which could have carried volatile compounds, might have contributed to the formation of a new atmosphere. Additionally, because Proxima Centauri is a red dwarf, Proxima b is likely tidally locked, meaning one side of the planet always faces the star while the other remains in perpetual darkness. This could result in extreme temperature gradients, with scorching heat on the star-facing side and freezing cold on the opposite side, potentially complicating the prospects for life as we know it. Understanding the timing of Proxima Centauri's activity, specifically its transition from an active to a quieter phase, is crucial for determining whether Proxima b's atmosphere could have had enough time to stabilize. If the high XUV radiation persisted for too long, it might have prevented the development of a thick, stable atmosphere altogether. Thus, while Proxima b remains one of the most intriguing exoplanets in the search for habitable worlds, its long-term habitability depends on a delicate balance of factors: the nature of its star's radiation history, the ability of the planet to develop a protective atmosphere, and the environmental conditions that may have allowed for the emergence of life. Future missions, such as observations from the James Webb Space Telescope, will be key to determining whether the planet's atmosphere, if it exists, could support life.